And we're going to react this piece of magnesium with some hydrochloric acid in this container, and it's going to produce a gas, and you'll find out what gas it is. You know what gas it is, but you're going to write it down in the balanced chemical equation. We're going to take the temperature of this water. We're going to read the volume of this water in this big long tube called a eudiometer, and I'll spell that for you later on the Word document. So we're going to read the pressure on this mercury barometer, which I've taken a picture of, and you're going to read to the nearest tenth of a torr using this vernier scale if it comes into focus. There we go. Right now, but it's going to be 690 something torr. It's between 690 and 700 torr. There's a better picture of it later. Ready? Okay, this is reacting magnesium, a 40.9 millimeter strip, and I've got the length of one long strip, and we'll do a proportion to find the mass of a small piece of magnesium. Got the data somewhere else later. I'm just videoing this part of the lab right now. So I'm going to react using a eudiometer. If you turn this around, can you point in here, camera person? In this pneumatic trough, can you see down here? Can you see that down in there, that little stick figure? That's where the gas is going to come out into this eudiometer, and we're going to measure the volume. And I've cut the piece of magnesium to be the right size. Just that's good. That's good. It's going to be the right size that it's going to make less than 100 milliliters of gas in the balanced reaction, which you'll see that in a moment on the Word document. So hopefully these bubbles will collect in the eudiometer and I won't have any error. There won't be a leak in the tube. There will not be a leak here. So I'm going to put it in here and quickly collect all the gas. 3, 2, 1, go. Do you see the hydrochloric acid reacting? And immediately you see the bubbles forming. Hopefully we won't have any bubble trouble in this lab. It'll just, all the bubbles will collect, and it appears that it's happening correctly. Then I'll do some cool things with volume and temperature using Charles' law, which is kind of cool and warm at the same time. So we're going to measure the gas temperature, the gas volume, and the gas pressure. Let's walk over here while this is reacting and read the barometer. This building was built in 1976, and I believe in the first or second year, I don't think you can buy mercury barometers anymore. They use a different oil inside those, but this is a old school, and I've got a picture of this where you can read it more accurately. It's between 6.9 and 7.0. It's between 690 and 70 torr. And here in Canadian Texas, at elevation of about 2,500 or so, most of my average readings are about between 690 and 710 millimeters of mercury, and I'll have the data on that later for the historical averages. But on a Saturday, October 10th at 8:53 in the evening, wow, that's how awesome my Saturday night is. I'm videoing a gas lab. I hope that got a reaction of some people. Okay, so we'll finish that. Looks like the bubbles are about done. And if you can see in here, this tiny strip of magnesium is just kind of like, what happened to it? And that's a good question. What happened to the magnesium strip? Someone a few years ago said, well, the magnesium's in this tube. I'm like, dude, magnesium's not a gas, dude. So we'll have to get a more accurate description. Can you see inside this test tube? It looks like that piece of magnesium is kind of floating there. And I'm shaking out the, shake, 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 shake your test tube, diddle-diddle-diddle, try to get all the bubbles in this eudiometer gas tube. So shake that down. So what's happening in here, we have what's in here. We will discuss that in class. This was hydrochloric acid. Now it's maybe some left, and it's probably excess reactant, isn't it? Yes, it is. It's excess reactant, and there's something else in here. This is not hydrochloric acid, dude. This is a gas. You're like, that piece of magnesium was tiny, but that's a lot of gas. Yeah, because the standard molar volume is 22 liters per mole. So yeah, we don't have a whole mole, or it'd be like I would need 22 liters, 100. I'd need 220 tubes. Like, well, I would fill it up too much. So this is only a very small fraction of a mole. In fact, so small we call it millimoles. So we'll measure how many moles of gas we have in here. And in a moment, we're going to take a picture of this. So I'm just going to go ahead and tell you, if I look at this eudiometer, it goes by 88, 90, 92, 94. So every 2 milliliters is 10 marks. That means it's 0.2 mils per mark. So this goes by 0.2 milliliters. Okay, that was 22.6 degrees Celsius. We read the volume, we read the pressure, and that will be in a Word document that you'll see in a moment. But I want to talk about volume and temperature relationships. As the temperature of a gas raises, its kinetic energy is moving faster, its kinetic energy raises. So temperature is related to kinetic energy. When you heat up a gas, it moves faster, and with a certain constant pressure, it tries to expand. Charles' laws, volume and temperature in Kelvin are directly related. So we're going to take this temperature in Celsius, make it Kelvin, but come in here closer and watch this line here. Or do you see that? I think it was about 92.4 milliliters. That's not important. Just keep that level. I'm going to put my hands on the rest of this eudiometer. My hands are about 37, 36 Celsius. This is 22.6 inside here. So I'm going to watch what happens when I put my hands on it. Do you see what's happening? Heat in my hand is expanding the gas. So it's now bigger, it's a bigger volume, 92.4 than this lab thermometer said. So it's more, more than 92.4. In fact, I'm reading like 94.4. So I raised it like 2 milliliters just by raising the temperature with my hand. That's amazing. So Boyle's law, pressure, volume are inversely related. Charles' law, volume, temperature are directly related. The good one, Gay-Lussac's law, pressure, temperature is directly related. And Avogadro's law, volume and moles are directly related. And of course, at STP, 1 mole of an ideal gas occupies 22.4 liters, or 22.414. But real gases are a little bit less because of intermolecular forces and the van der Waals equation instead of the ideal gas equation. We'll talk about that later. Thanks.